We will finish up this discussion with a discussion on mirrors. And mirrors are in many ways similar to lenses in terms of the calculations and also in terms of how various mirrors act, converging versus diverging. You just have to remember when you're looking at a mirror that a diverging mirror looks very much different than a diverging lens, and a converging mirror looks very much different than a converging lens. A diverging mirror is convex. A converging lens is also convex. A converging mirror is concave. A diverging lens is also concave. So there's those differences, but most of the calculations are almost identical. So let's take a look. First of all, when you look at an object on a flat mirror that's reflected back into the observer's eyes, the observer is seeing a virtual image. He is not seeing a real image. This image cannot be projected over on the side of DI. Now this is a diverging mirror, spherical mirror, and you can see that it's actually concaved in appearance. And what it does is it causes a focus of rays on the focal point, which is defined in the same way, but also notice it's on the same side because it's a mirror as opposed to a lens. So when you have parallel rays on a large spherical mirror, they don't cross at a common point. But if a spherical mirror is small compared to its radius of curvature, then the parallel rays will focus on a common point known as the focal point, and that the distance from the center of the mirror to the focal point is called the focal length. This is a converging mirror. It has a positive focal length, and if described, it would be described as a concave mirror. Now, parallel rays striking a convex mirror or a diverging mirror will scatter the way they're shown here, but they do focus on a point on the other side. And in this case, the focal length is now negative. Now, there are several cases that we can talk about in terms of what happens with mirrors. In the first case, if the object is beyond the focal length, so it's farther from a converging mirror than the focal length, then this is what you'll always get. You'll get an image that's even farther away from the focal length. It will be inverted and magnified, just like it's shown here. The principal rays can be drawn in very much the same way, except they're reflected instead of passing through, instead of refracted. So the parallel ray 1 strikes the mirror and then goes through the focal length. Parallel ray 2 strikes the center of the mirror and has an angle of incidence and an angle of reflection that are the same. Ray 3 goes through the focal length, strikes the mirror, and then comes out parallel. And those three intersect together to form the image. Now really, you only need two of these three in order to draw the image and determine its height. Now case 2, remember case 1 was where the object was farther from the mirror than the focal length. Case 2 is when the object's closer to the mirror than the focal length. Now in the first situation, you had a real image. In the second situation, you now have a virtual image. What happens is you strike the parallel ray 1 goes directly through, is parallel, strikes the mirror and then goes through the focal length. Ray 2 goes straight into the mirror and out, and then ray 3 travels up and then goes parallel so that it goes through the focal length. You can see the focal length being behind, and then those three are extended by dashed lines to actually form the image, which is virtual on the other side of the mirror. Case 3 is when you have a diverging mirror. You have a diverging mirror in which the actual object is farther away from a convex mirror than the focal length. And you can go through these rays again. I'm not going to go through them in detail, but you can see that you end up with a virtual image that is smaller than the object and it's upright. And this is actually an example. B is an example. These mirrors are used to survey a store for shoplifters. And the reason they're used is you can put a very large, see, it compresses because of the smaller image. It compresses everything so that you can see more with one mirror. That's why some of the mirrors will say objects may be closer than they appear, because they don't appear as close as they really are. So let's take a look at some problems. And these problems are very similar to the problems that we just did, but now we're talking about mirrors instead of lenses. An object is placed 40 centimeters in front of a concave mirror with a focal length of 20 centimeters. Where is the image formed? What is the magnification? And describe the image. Now, based on, this is a case one situation, so you can sort of think about it, because it's beyond the focal length. So you're going to have a real image that's closer to the mirror and that's going to be inverted and small. So let's see if that's how it works out. So we use the same formula, 1 over d0 plus 1 over di is equal to 1 over f. So, which means that d0 is 40 plus 1 over di, and it's a normal or concave mirror, converging mirror, so it's going to be a positive, so it's going to be 20. Now, if you do the math here, I think you can see that di is actually going to be 40, because 1 over 40, this is 2 over 40. So 2 over 40 minus 1 over 40 is 1 over 40. The magnification is going to be 40 divided by 40, or 1 minus 1, so it's going to be inverted but the same size. And because this is a positive number, this is a real image, this is going to be inverted, but neither magnified nor compressed. Now let's take a look at this second one. A concave mirror with a focal length of 20. The image is formed minus 10 centimeters from the mirror. What is the mirror's distance? What is the object's distance and magnification? Okay, the fact that it's closer and minus tells you it's a virtual image, so it's very likely the object is within or closer to the mirror than 20 centimeters. Okay, so let's do that. We have 1 over d0 plus 1 over di is equal to 1 over f. Again, we have 1 over d0. Now it's going to be minus 10, so that's minus 1 over 10 is equal to 1 over 20. So this is going to be 1 over d0 is going to be 1 over 20 plus 1 over 10, or 3 over 10. 3 over 20. So d0 is 20 over 3, or 6.66 centimeters. So it is closer than the focal length. The magnification is di divided by d0 minus di divided by d0. So that's minus 10 divided by 6.66. So m is going to be a positive 1.5. So this is going to be, because this is negative, it's going to be virtual image. Because this is upright, or this is positive, it's going to be upright. And it's going to be magnified. it doesn't tell you what what the size of the image object is, so you can't do that, but it's going to be magnified.